So this video is on the classwork 10-74 to 10-78, where we're going to be talking about semicircles and what is true about inscribed angles in a semicircle, and also what is true about quadrilaterals inscribed in a circle, and what is true about two chords intersecting in a circle. So in this first problem, we're going to be dealing with semicircles. And so in the diagram, they are telling us that the measure of arc QR is 180 degrees. So this arc right here, QR, let's see, let me do it in the color we can see, not black. This arc right here, QR, is 180 degrees in terms of its measure. Now they're asking us what has to be true about the measure of angle P and why. So the measure of angle P is right here. It is an inscribed angle that intersects at the circle at Q and R, forming this intercepted arc with a measure of 180 degrees. When you have an inscribed angle that forms an intercepted arc, it is half the measure of the arc. So that means that this is going to be 90 degrees. So the measure of angle P is 90 degrees. And again, the reasoning behind that is because it is half of the intercepted arc that it forms. Okay, so it is half of the intercepted arc that it forms. Okay, the next question says, if you drew QR, what would be special about it and why? So if I draw QR, what's true about QR is that this is going to split this into two semicircles. Number one, since this is 180 degrees, this side also has to be 180 degrees because a circle is 360 degrees. So this has to be the rest of the 360, which is 180. It also is the diameter of the circle. So two things that it is. QR equals the diameter. Also, it splits the circle into two semicircles. If point P was moved to a different location on the circle, would the measure of QR of QPR change? Sketch circles with point P in three different locations and justify your answer. So here they want you to draw three situations. I'm going to visually show us. So let me get that up for us. So in this situation, I have made this be a diameter. Okay, this is a diameter. And as I drag this point around, this angle is not changing. The reason it's not changing is because as I drag this, it's still connected to here at this point, which in our picture is, let's say, Q, and here to this point, which in our picture was R. So this, which was 180 degrees, doesn't matter where I drag this to, since it's forming that intercepted arc of 180 degrees and it's an inscribed angle, it's always going to be half. And you can see that this is a 90 degrees when you're looking at it. Same as if I was to bring it to the other side, the other half of the circle, same situation. So again, here they wanted you to draw 3 circles with the point P in 3 different locations, but still connecting to, QR, because it's still in OQPR, and justifying that. Okay, just like I showed in the picture. So on D, in the diagram at the right, UV is a diameter. So this is a diameter. We want to know what kind of triangle is triangle UVT. We also want to know why. Then if we know this is TU is 6 and this TV is 8, what is the radius and what is the area? So if this right here is a diameter, that means that it's cutting this circle in half. Okay, so this half and this half. Now the half I'm concerned with is this side over here. And that, again, since it is cut in half, is going to be 100, let me zoom in here, 180 degrees. Now, this intercepted arc here, it's intercepted by that angle UTV, which means it's going to be half of 180 degrees. So it is going to be a right angle. So when they ask you what type of triangle this is, triangle UVT is a right angle. Right triangle. Since angle UTV is an inscribed angle forming the intercepted arc UV. Let me do it like this, which is 180 degrees. So angle UTV is half, I should say measure, of angle UTV. So the measure of angle UTV is half of 180 degrees, which is 90 degrees. Now, since we know this is a right triangle, what that allows us to do is use Pythagorean. So if I know that this is 6 and this is 8, and we're trying to find this diameter, some of us might recognize this as a 3, 4, 5 and understand that that D is going to be 10 due to similar triangles. However, you can do 6 squared plus 8 squared equals D squared. We get 100 is equal to D squared. So D is going to be 10. Now, if your D is 10, that's not what they're asking us for. They're asking us for the radius. So the radius is going to be half of that, which is 5. Then they're asking us for the area. And the area is pi r squared. So this is going to be 25 pi. Now on 10-75, this time we're dealing with a quadrilateral that's inscribed inside a circle. And they want us to figure out what x has to be. So a couple things I notice, okay? I notice that this 100, which meets here and here, is forming this intercepted arc here. And so that arc that's formed by that 100-degree angle is going to be twice that. So this is going to be 200 degrees. Now, if that's 200 degrees, that means this this arc is going to have a measure of the rest of 360 degrees, which is going to be 160 degrees. Now, if that is 160 degrees, this angle here BAD that forms that intercepted arc of 160 is going to be half of that, which means it is going to be 80 degrees. So X is equal to 80 degrees. Now, Alejandra notices something. I think that the opposite angles of a quadrilateral, and this is the key here, inscribed in a circle, are always supplementary. Supplementary is when they add to 180 degrees. So this 100 plus 80 is 180. And in a quadrilateral, we know that one of the formulas for a quadrilateral to figure out the sum of all the angles is your sides minus 2 times 180 degrees. That's going to be 2 times 180 degrees, which is 360 degrees. So we know all the angles in a quadrilateral add up to 360, which means these ones also have to be 180. Now, maybe that just happened for this case. How can we prove this? So to prove this, what we're going to do is the following. So if we take a circle, okay, I'm going to zoom in a little bit. If we take a circle and we have a quadrilateral in here, and we are trying to figure out the relationship here between opposite angles. What I'm going to do is I'm going to call this one, let's say X. Okay, this angle here that I'm drawing in red is X. So what does that mean? Well, it means that this intercepted arc here, due to that inscribed angle, is going to be double that. So that's going to be 2X. Now, if that's 2X, the rest of this circle is going to be 360 minus 2X. That's what the length of that measure of that arc is. So this opposite angle here, which is forming the blue intercepted arc, is going to be half of that. And half of 360 minus 2X is 180 minus X. So now if I take those two angles and I add them up, I'm going to have X plus the other angle, which is 180 minus X. Together, the X and the minus X are going to cancel out and you get 180 degrees. So it does not matter what that value is. Every single situation is going to end up with the opposite angles in a quadrilateral that's inscribed in a circle, adding up to 180 degrees. So on 10-76, Timothy asked, what if two chords intersect inside a circle? Can triangles help me learn something about these chords? So we're looking at this chord AB and this chord DC, and we're trying to figure out if there's any relationship that we can come up with. So let's say I have this chord right here for DC and this chord right here for AB. And we are going to make some triangles. So one triangle I'm going to make is this one right here. And then I'm going to connect AC and make another triangle. Now, one thing I know has to be true here is that these angles here, this angle here and here have to be the same. Why? Vertical angles. Okay, vertical angles. So I'll just color code the reason. Vertical angles. That's why those two angles are the same. Then if I'm looking at this, I notice that I have this arc being formed. I'll draw it in, let's say, blue. So I have this arc being formed right here. This arc being formed arc BC. Now it is formed, I'm going to highlight, by two different inscribed angles here. So this one here is going to form that, so that's BDC. And I'll do it in a different color. This one here is going to form that same one. So that means that those two angles are going to be the same. So let me just undo those markings. So it means that this angle here, I'll do it in teal, and this angle here are going to be the same. And why? They form the same intercepted arcs. So they will be the same value. We saw that the other day. Now, I have a situation where I have two triangles that are going to be similar. They're going to be similar by angle similarity. Okay. So they asked us here, I guess I jumped ahead a little, to compare angles B and C and decide which one's larger. And D and A. I show that D and A, the measure of D and the measure of A are going to be equal. Okay, so they're going to be equal to each other. If we take a look at a difference, so we want what B and C. So let me draw in this B and C, this right here. That's the arc that's going to be formed when I am dealing with angle B, okay? But it's also the one that I get when I'm dealing with angle C. Both of them are going to form it, okay? So again, this angle B forms that arc, and this angle C forms that arc. So those are also going to be the same measure. So I will put it in there, but at this point, I already kind of knew they were because of having angle. I use the vertical angle. They're using those two angles. So this angle here and this angle here are going to be the same. So I know the measure of angle B is going to equal the measure of angle D. Again, because they form the same intercepted arcs. So how are triangle BED and ACEA related? As I set up here, they are similar by angle similarity. If DE is 8 and AE is 4 and EB is 6, what is EC? Show your work. Okay, so I'm just going to redraw this picture. So I drew the picture out here and put in 8 for DE, 4 for EA or AE, 6 for EB, and I'm going to call this X. Now we know these triangles are similar, and we know that they're similar in this particular, order. I know that BED is similar to CEA if you look at the angle marking. B and C correspond, E and E correspond, D and A correspond. So I'm going to write underneath it just to match it up. So this matches with CEA. Okay. So when I have DE, okay, DE, DE. DE is going to match up with EA. So DE and EA are going to be corresponding ones. Those ones are corresponding. When I'm looking at this and I'm looking at BE, okay, so I'll circle that since I've already drawn in the other color. So when I'm looking at BE, this is BE. So that's going to match with CE. So BE is going to match with C in terms of corresponding. So those are corresponding sides. So what I know is I need to figure out using proportions what C is going to be. So when I do that, I'm going to take, let's say 8/6 equals 4/x. That's one proportion I can set up. So I'm going to get 8x is equal to 24. So I get x is equal to 3. So in this situation, this x right here is going to be a 3. Okay. So that's what EC is. Now, something that you want to notice here. If you take a look at DE, which all the way across is 11, and you take a look at BA, which all the way across is 10. I'm not concerned with the 11 and the 10. What I'm concerned with is the amounts that I got in the segments. So what you'll notice here is here we have 8 and 3. Here we have 6 and 4. There's a relationship between 8 and 3 and 6 and 4. 8 times 3 is 24. 6 times 4 is 24. So what happens when you have two chords intersecting, the segments that are formed, if you multiply the segments that are formed by the one chord intersecting and the segments that are formed by the other chord intersecting, they're going to equal the same thing. So that's also something we want to come across with from this lesson. On this problem here, we are dealing with a situation where P is the center of our circle. We have these endpoints L and M, which are chords, okay, which is a chord. They want us to figure out a couple of things. Number one, we know that this arc LM is 150 degrees. So this is going to be 150 degrees for its measure. We also know that the radius of the circle is 6. So I'm going to draw from here to here, and I'm going to label that 6. I can also draw from here to here. I also know that in this situation, that angle I just formed at P is a central angle. And so that central angle here has to also be 150 degrees. Now, what's going to happen is we are going to take this and I'm going to draw a radius from here to here in a way that it intersects that chord at 90 degrees. We saw that when that happens, that is when a radius or a diameter, any line that goes through the center of your circle intersects a chord. Remember, it cuts it in half. So it's a bisector, but it also does so in a perpendicular manner. So when I'm drawing this, I'm drawing it to be perpendicular. So that means that this is going to be 90 degrees. So what I just discovered is I now have a right triangle. And in that right triangle, I have this 90 degrees. This is my hypotenuse, which is 6. I don't know anything else in terms of sides, but what I do know is since this is splitting this in half, it's also splitting this angle in half. So if this was 150, then this is going to be 75 degrees. So when they want us to figure out the length of LM, I'm going to figure out that half, and I'm going to use trigonometry. And so from 75, I have opposite over hypotenuse. So I'm going to do sine of 75 degrees equals opposite over hypotenuse. So 6 times sine of 75 degrees is equal to x. And so I'm going to put that into my calculator. Now the calculator I'm going to use is Desmos here. If you're using Desmos, click on the graph settings. Make sure you change it from radians to degrees before you do any calculation. So I'm going to do 6 times sine of 75 degrees. And I get that the line segment is 5.79. So let's say 5.8. 5.8. Then I am going to double that because that is going to be this portion, but I want the whole length. So I am going to double that. But first, let me write that my x is going to equal 5.8. So again, when I double that, so I'm going to come here and times this by 2. I end up with 11.6 for my answer. So the whole length of LM is going to equal 11.6 units. What if you know the length of the chord? How can you use this information to reverse the process and calculate the measure of the arc? Draw a diagram of a circle with a radius of 5 units and a chord AB with a length of 6, and we want to find the angle measure. So I drew the picture. We have a circle with radius 5. We have a chord AB that has a length of 6, and we are asked to find this arc measure. So what I'm going to do is what I did in the last problem. I am going to draw a radius that is going to be perpendicular. So since I'm making it perpendicular, okay, that means it's going to cut that chord in half. So one of these is going to be a 3 and the other side is going to be a 3. It's cutting it in half. So now I have a situation where I have 2 sides of a triangle. The other side would be a 4 if I wanted to find it, but they don't want me to find that necessarily. What I need to find is this angle right here. I want to find that angle because that's going to help me find the measure. So to find that angle, let's say I call it theta. I know from this angle, I know opposite and hypotenuse. So I'm going to do sine inverse of opposite, which is 3, hypotenuse, which is 5, and I'm going to get that angle measure. So when I do that, okay, I'm going to do sine inverse of 3/5, and I'm going to get 36.87, let's just say 36.9 degrees, okay? 36.9 degrees. So that is that angle, which means that the whole entire angle is going to be double that. So this whole entire angle, I'm going to double that. I'm going to times this by 2. And when I double this, okay, I times this by 2, I end up with a 73.7, okay, 73.7 degrees. Now that's the angle for a measure for the central angle, but that's also the measure of my arc. Whatever the measure of the central angle that forms that arc, that's also the measure of the arc measure. So measure of arc AB is 73.7 degrees. Now here, we're going to be using these ideas to help solve these. Now, in this case, these intersect. I know that we have 3x and 2, and I want to solve this if I know that KL is 8. So if I know that KL is 8, I know that this has to be 6. Okay. Now I can do this using congruent triangles. I'm not congruent triangles, sorry, similar triangles. Okay, where I connect these, and what's going to be true is this angle here and this angle here are going to be the same because they form this arc. Okay, this arc. I also know that this angle here, I'm just going to do it in a different color, and this angle here are going to be the same because they form this arc. So they have to be the same as each other. So I have similar triangles. And if I'm looking at this, I know that this 6 is going to correspond with this x. This 3 is going to correspond with this 2. So I can say, using similar triangles, 6 over, let's say 3, using it from the same triangle, and what corresponds with this 6 is going to be this x. So I'm going to say x over 2. I cross multiply and solve. I get 3x is equal to 12. I get x is equal to 4. So this is a 4. So what is always going to end up happening here is whatever the product of these two segments are, it's going to equal the product of these two segments. So I also could have, and hopefully now on, and look at this and go, okay, 6 times 2 equals 3 times x. So 12 is equal to 3x, so x is equal to 4. Letter B, RT is a diameter. So since it's a diameter, I know that that's cutting this into a semicircle. Okay, it's cutting it in half. So this is 180 degrees, which means this has to be a right angle. So I have a right angle here. And they want us to find x in this situation. Now, what I know is true here is that in this right triangle, let me draw out this right triangle. Okay. Again, this is the angle I'm trying to find right here, that x. I don't know what this is. Let me call it, I'll just use some other letter. Let's say A. But I know that this is double that. How do I know? Because I have a single mark here, a single mark here, a single mark here. So whatever this is twice as long. So you might recognize this as a 30, 60, 90 right triangle. So in this case, the side across from the hypotenuse, from the 90 degrees is your hypotenuse. Your 30 degrees is always opposite that. So that's going to be 30 degrees, which means my X is going to be 60 degrees using the idea of 30, 60, 90. On letter C, they want us to find this arc measure over here. That's what they want us to find. Now I can find this arc measure here because it's formed by that inscribed angle that's 52 degrees. So if I double 52 degrees, I get 104 degrees. Now I can take that 104 along with this 131, and I know that a circle is 360 degrees. So if I take 360 degrees minus my 104 minus my 131, I am going to get my X. So 360 minus 104 minus 131 is 125 degrees. So that's what X is. So in summary, some of the ideas that we have learned here, okay, maybe I'll add it on to the next page. So one thing we learned is that if we have a diameter where in a circle, it basically cuts a circle in half and we get a semicircle as seen here. Any inscribed angle, okay, I don't care where the point is, say it's over here. If that inscribed angle forms that ends up reaching the endpoints of my diameter, basically, you will always get a 90-degree angle here. Why? Because it's going to be half of the other side of this circle, which would have been 180 degrees. Okay, that's always the situation. But basically, if you have a semicircle with an inscribed arc inside that semicircle, sorry, an inscribed angle inside the semicircle, it is always going to be a right angle every single time. We also saw that if we have a quadrilateral inscribed in a circle, that what's going to happen is the opposite angles are going to be supplementary. So this angle here and this angle here, which are opposite each other, and this angle here and this angle here, and maybe I'll do these are all different angles from each other. So I don't want to imply that these are the same. Okay. But what happens is if I take the measure of angle D plus the measure of angle B, since they're across from each other, they're supplementary, they add to 180 degrees. If I take the measure of angle A plus the measure of angle C, they also are going to be supplementary, add up to 180 degrees. Okay, that is true when you have a quadrilateral inscribed inside a circle. Something else that we saw is when we have two chords intersecting in a circle. Okay, we saw that they were similar triangles that were formed if I connect from here to here and here to here. But another way of thinking about this is when these two chords intersect, the two segments that are formed on the one chord and the two segments that are formed on the other chord. So here A and B are formed when this line cuts through it, and C and D are formed when this one cuts through it. What is always true is that if you take A times B from the one chord, it is going to equal C times D from the other chord. So again, this chord here is intersected by this one. It's split into these two pieces. If I take the product of these two pieces, it's going to equal the product of these two pieces every single time.